Okay, welcome back to this morning session. I would now like to demonstrate on the blackboard the situation of a component containing a crack and what we can do. Oh my God. What we can do to keep the component under safe conditions. So I'm drawing a diagram which shows stress as a function of crack size, and I'm demonstrating this in the frame of linear elastic fracture mechanics because it's easier to show. We have simple formulas which we can resolve for any parameter within the formula. It works for everything, of course, but here it's easier to demonstrate. Now we start with the core equation. Stress intensity factor is sigma applied sigma times square root pi a times the y function. Okay. And for the critical condition, the crack driving force is equal to the fracture toughness, K sub C. And then the stress assumes a critical value, and from this we solve for sigma C, which is Kc divided by the rest of the equation, so very simple, and that's it. So this is a parabola, and sigma versus A with a 1/2 power, and the parabola, my color chalk didn't find it yesterday. It has disappeared, evaporated. Okay. So we have a parabola, and which looks kind of like this. So this is this equation here, sigma C equal to Kc divided by square root pi a and y. And this is failure condition, which we hopefully will never reach. In other words, our component has to stay below that curve all the way through its life. And now let's assume that what I call the service point, applied stress, maximum applied stress. We have variable stresses because we don't have to forget about fatigue. The maximum stress, and here sigma component, whatever it is, however it's defined, it doesn't matter. And here we have the crack size A component. Now it's either found, looks as if you can't read it. I mean, I know my handwriting is no longer as it used to be. It was in the past. It was even worse. Can you read it? It's a bit hard. Just complain whenever you can't read something, you don't understand something. Raise your hands and say, okay. So this is our service point. which is supposed to be below the failure line. And the crack is either found by NDI in a structure, which is no easy task, by the way, and or it is assumed in the design stage. Not only in the design stage, but also something is already in operation. You find a crack, but nevertheless, your structure is now has an age of 20 years or 25 years, and you scratch your head and ask yourselves, what would happen if I would find a crack here at the critical location with high stress location, and what is the crack size that I can find, and what would then be the remaining lifetime? Now, this shows that we have a safety margin as compared to the failure line. A safety margin in terms of stress or load here. So it's the vertical distance. And if you would get too close in the vertical direction, then we have to ask ourselves, what can we do? There are several measures that can be taken. Either you have found a crack and you repair it, you do a repair weld, which sometimes makes things worse than ever. When the crack is in a weld and you do a repair weld within a weld, this has to be carefully repaired, particularly if it's a thick section. Can repair it, or a popular method, by the way, is when you have a crack, you drill a hole into the crack tip. So you drill it away, you machine the crack tip away, and either the crack stops forever, or it takes some time until it reinitiates, and so you gain life. So this is a popular trick. Or you reduce the applied load. This can be done, for example, when you have a pressure vessel. You attach a belt, steel belt, or whatever it is. And please, pressure vessels are not only thick-walled stationary structures. You need also pressurized components in aerospace structures. See rockets, you know, and or the combustion chamber of an aeroplane turbine. And once I was sitting in an aeroplane when just after takeoff, one of the two combustion chambers exploded. This is a very nice experience, I can tell you. Knowing that for the same reason previously two planes crashed, one in Birmingham and one in Zagreb. But I'm still here to entertain you. Or reducing the stress, for example, you have a bridge which is used by vehicles. You can set up a marker saying the maximum allowed weight is so many tons. So you reduce it from the previous one, hoping that all the truck drivers obey. But reducing the applied stress is really certainly an effective method. And by the way, belt around the pressure vessel, shut it off. Shut it off for the whole, please. In many cases, most cases, there is an escape out of a problem, but you shouldn't be panicked when there is a problem arises, as most cases. Okay, so this is the safety margin in terms of load, applied load, or internal stresses, or whatever it is. And there's also a safety margin in crack size, AC, a critical. So the crack can extend from the service point to AC. And hopefully the time from here to there is sufficiently long for the reasons that I explained before the break. The crack can, now it's going to be messy now, lifetime, quotation mark, the crack extends by, not a reference line here, by fatigue, corrosion, and or creep, high temperatures in aero engines, for example, or a combination of all three nasty things. You have aero engines, you have the gases, and which cause corrosion, hot gas corrosion. You have creep due to the high temperatures, fatigue anyway. And so the producers have very complex test stands where they test the materials. And so this shows, or is supposed to depict what happens, what kind of problems we have to and we can solve at the end. So we can determine critical conditions, either for a given stress, the critical crack size, or the problem is when you solve for the critical crack size, this can't be done in an implicit way because the crack size sticks also in the right function here. And if it's not a simple equation that can be solved for A, you have to do an iteration. So although it looks simple, it's not that simple. Now, but this is not the only way to determine critical conditions. I told you on Monday morning that thin wall structures, failure conditions are characterized sometimes by large amounts of crack propagation, can be really large amounts. And so in that case, we use the R-curve, something that you do already know. So crack size and here crack resistance maybe in terms of K, and the R-curve maybe here. So this is A0, a found or assumed crack size. And then we construct the tangency condition. Now it's no longer a straight line. On Monday morning I did this analysis using the energy way to talk about fraction mechanics. Here we are at the stress level. We have no longer a straight line. We have something like a curved curve. And this is then the critical stress. You remember the critical stress or force or whatever we label the diagram here. And at the same time, we find the critical crack size, which can be the order of centimeters or tens of centimeters or whatever, so quite substantial. There's another thing. We can use the same construction if we ask what is the crack size I have to find. So I have in my mind I have the R-curve and I have the applied stress. I do this, I draw this line here, the stress line, critical applied stress line. And then I shift the R-curve far enough that I reach tangency condition. So, you can play around with these things. I've written a handbook where all these little details are explained. And, I think it's in your literature list. Okay. we should keep in mind that the R curve here, living with R, is a material property, and the driving force curve is a property that depends on geometrical parameters for a given stress. So with another geometry, you have another correct driving force curve. For short cracks, the tangent condition goes down, and for longer cracks, the tangent condition goes up. It can be easily seen by the geometry of this construction. Now, coming back to one of my favorite topics, look at the problem in as many ways as possible. Once again, here I have my R curve design construction, A and K, and what did I do? And so this is the R curve, and here we have the applied stress or force. I'm using now the force symbol. It doesn't matter whether I use force or stress, it is just the applied load, okay? And so here, this is a critical one, but the same situation can be shown in another diagram. Force versus any kind of displacement. Doesn't matter where we measure it, it should just span the crack, we measure across the crack. And we have this relationship, the roundhouse curve. And this is the critical force. So this shows the same situation, okay? Now, Monday, I try to explain to you the two limiting loading conditions, load control, force control, and displacement control. Please, there's always a little bit of confusion, and unfortunately, I do run myself into the same trap very frequently. You're talking about load. Loading. Load. Loading is okay. What is load? Some people send me diagrams in their manuscripts for publication. Load, comma, kilonewtons. This is wrong. Load can be force, can be stress, can be displacement, can be whatever, you know, whatever loads the material. So we have to be specific. We talk about plastic limit load, which is a mechanical quantity. It should be limit force. That's why I introduced in our methods the term force with the symbol F. And F, not P. F is standardized by ISO for force and not P. And that's why I also said the yield F sub Y is a yield force. Your load is not only misleading, it is wrong. Full stop. So this is once again the same situation. Now back to force and displacement control. And why is this? I'm drawing this diagram here. Normally, the specimen should go, or test piece or component should get unstable here, because you can't increase the force anymore. Why does it go down here? It does only work when we have a displacement control, or a relatively stiff machine, or electronically controlled displacement control machine. And the reason is the behavior of the crack driving force curve. So this is A, and here I have my R curve, and here I have the crack driving force. In whatever terms, say K or J or G, it doesn't matter. So under force control, we have this force control, this behavior. So the driving force increases with crack size. But for displacement control, remember the DCB specimen that I showed you on Monday afternoon that is used, that is loaded. We can load a specimen, please. We load a specimen using, applying a force or a displacement. So loading is not to be confused with load. The specimen that is loaded by turning two screws against each other, it is there where the crack driving force decreases with increasing crack size. So the crack driving force curves, that's why it's stable. The slightest amount of crack extension would run into lower amount of lower magnitude of crack driving force. But in all the textbooks that I know, they come up from infinity, which is not correct. Of course, they have to emerge from the origin here, and so it goes down here. Okay, so there must be a maximum. It can't be anything else. And I must admit, I found that very late when I drew my diagrams, delta 5 as a function of the applied strain, and then you can easily show that this has to start at 0. And this also shows that even under displacement control with a very stiff machine, the specimen can become unstable if the crack is very small, very short. You see, would I shift the R curve far to the left-hand side, I would reach tangency condition. So I've never seen any kind of textbook. They all come from above, from heaven, you know. Few words. I mean, most of this comes again in new graphs, but not everything that I'm drawing here on the blackboard. Sometimes during my presentation it comes to me that I have to fill a gap and I need a blackboard to draw it on the blackboard, and so it's happening here too. And as far as residual life is concerned, residual life for a cracked component, remember we are now only talking about fatigue, forget about the other mechanisms, only fatigue. We have a crack propagation curve. Oh, sorry. How did we determine the crack propagation curve? We measured in an experiment A over the number of load cycles for various stress cycles or whatever, and here we end up with this nice S-shaped curve, logarithm of delta K, logarithm K dn. So all these curves collapse into one curve if we do it properly. And so this is our material property. And we have a crack propagation equation. For example, here in the middle is the center region where we have the power law, the A, the N. The A, the N is C times delta K raised to the power of M. Once again, the power of M is mostly between 2 and 4, not exclusively, but mostly. Now, how can we determine residual life? Any idea? We find a crack, size A0. How do we determine lifetime? In principle, I mean, what do we have to do to find the residual lifetime? Any idea? I know it's close to lunchtime, but I'm hungry too. We determine this curve by doing the derivative of these curves. Now we have to go the same way back. Okay. We have to go the same way back. We have to, for a given delta sigma, of course, otherwise it would make sense. In principle, we reconstruct the AON curve. So we go the same way back here. For example, to stay here within the Paris region, we may have, the sketch is not so nice, we may have an initial crack size that in combination with the applied delta sigma gives us a point where we enter the diagram here, okay? And then we go up the diagram until specimen fractures. So we can use the straight line relationship till a final fracture because here this is logarithmic scales. The percentage of lifetime spent here is just, I don't want to use that word, it is not so nice, but you know, when a fly leaves a little point of shit, it is not more than that. It's just the thickness of a line you draw, so it doesn't matter. Unless we only have, work only here in this region, then we have a different story. But we are talking about relatively long living structures, and so we enter here, and we reconstruct. I'm drawing a new line, a new diagram because it's getting too messy. Here's A0 that we found, and now what do we have to do? Everything has already been said. We go the same way back. I gave you all the keywords. We did the derivative of the AON curves in order to end up with the ADN diagram. We have to integrate the curve, of course, which for this power law, as we will see later, is still relatively easy, but when you have a more complex equation, we have to do it numerically. Okay? So we reconstruct the curve and here is a failure point where K has reached Kc, so this is the limiting condition. And here we have a critical, and so this is then the remaining lifetime. Or had we entered the diagram here, and this would be the remaining lifetime. So you can play around with these things. It is very, very basic. And then, for given crack sizes, you can determine the life of a material or a component, and you can construct SN curves, including endurance limit. I'm now going out of your picture. It makes me nervous.
Microphone is a problem.
Excuse me?
Microphone is a problem.
Microphone,
It's
yeah.
directional
Okay.
microphone.
Not every word that I say is worth being said. I can't say you know, I have to walk fast. And it makes me nervous that I don't sit all the time I lost it. No, I don't want to say. I think it's lunchtime. So we redo the AOS curve for various candles or various delta sigmas. We can determine kind of an SN curve, and if we take a more sophisticated equation, the NASGRO equation that I showed prior to the break, then we can even start with the threshold value, and we can determine the SN curve, including the endurance limit. This is what the Norwegians have done many years ago for offshore platforms. The interesting thing, sometimes I must give you the stories that I have on stock. You may know that oil drilling and oil production started in relatively shallow and quiet waters with the Arabian Gulf and later the Gulf of Mexico. At least in the Arabian Gulf, as far as I know, there were no major fatigue problems, but the big fatigue problems arose with the first platforms in the North Sea or even in the North Atlantic. Even the North Sea, although this is still quite a shallow sea, I think the greatest depth is about 300 meters or so. These are harsh environments with low temperatures and strong storms, high waves, which exert terrible forces, fatigue forces, onto the platforms, the stationary platforms. And so it became immediately evident that they're going to have a fatigue problem. In particular at the welds. The weld is always a critical part of a component or a system. And so the Norwegians and also the British did an awful amount of tests and also analysis. And particularly, I remember the Norwegians really did predictions for various shapes of welds. You know, the welds are not equal. You have butt welds, you have whatever kinds of geometries, you have T-joints and so on and so forth. And so they did kind of SN curve predictions, starting with different crack sizes, and for, like I said, for different geometries, which was really a very, very good job. So, and the same will happen to the wind parks, the offshore wind parks. They will hopefully learn from what has done for the offshore platforms. And the interesting thing is that sometimes the learning effect is almost absent. When there is too long a time span between the time when people have learned, have created a lot of knowledge, and when later, maybe 20 or 30, 40 years later, everything has to be done anew because people have forgotten about what happened in the past. This happens. Okay. Yeah, so we redo the A over N curve. This is the principle of which we can also explain later the methods of the procedure with which we determine inspection intervals. Okay, going back to high-tech. This is the equation that we can use for integration purposes to determine the life of a cracked component. And this is what I showed on the blackboard here, slightly nicer way here, and showing all the details that I already told you. Once again, tangent condition, this is increasing applied load, either in terms of force or stress or internal pressure. You see my hand drawings are not so nice, but I hope you see what I mean here. Once again here. Now this shows what I also demonstrated. This is load dependent, and here is load. This diagram is not for me. If it were for me, there would be stress or force or whatever. Stress intensity factor, and here is the procedure how you can determine initial crack size. And this is typical of lightweight structures, a stiffened panel, and so here is the characteristic width in terms of 2W. And here we have the yield strength, light stress here. This is the failure stress of the stiffener as a function of crack size, of course, here. And here is the failure stress of the skin, which raises because when the crack approaches, the crack size here, the crack approaches the stiffener, the skin is supported by the stiffener, and this shows what may happen when a crack in the sheet becomes, the skin becomes unstable. If instability occurs here, the whole thing becomes unstable because the increase in crack size jumps from here to there. We also hit the fracture line of the stiffener and the thing goes bang. So if instability occurs here at a lower stress, then the crack jumps. But it hits this curve here, which is a rising curve at this point here, so the system is stable. So even an unstable crack can become stable if it hits an area where the fracture strength, so to speak, increases. This was also, by the way, another story, lightweight structures, the nuclear reactor pressure vessels. some kind of safety philosophy was set up. Number one, we don't have cracks, which has to be achieved. But if we had cracks, they would never propagate. If they would propagate, they would never become unstable. If a crack became unstable, it would be arrested somewhere. And the idea is not too bad, because when you think of a pressure vessel that had seen long service, the inner part of the wall may have been embrittled a little bit by the neutron bombardment. So this is where a crack could become unstable, but arrested in the rest of the wall thickness is really big, and where the material has a higher toughness. And it could be that studies have been done, the details I don't remember because it is long ago, and this is in principle possible. Although it sounds a bit silly, but this is really a useful safety philosophy. You aim at having no cracks, you know? And then you do an analysis, had you ever a crack, would it really propagate, and so on and so forth. So this is, oops, that's the same again. Now, what I just was saying, the blackboard here, or what is the residual lifetime? We integrate the crack propagation equation, and we start from A naught, and as the lower integration bound, and the upper integration bound is given by the critical crack size. Then it becomes a bit more complicated. So I've done it for the Paris equation, very simple, and when you integrate, you solve the equation for n, which means that everything becomes upside down. So the important stuff in the end stays in the denominator. Here are the constants. Here is the integral from A0 to AC, and here is the crack size, and here the integration has been done. We have K matrix, here KC, fracture toughness. Here is maximum stress occurring in the structure. This is the critical crack size, the upper integration limit, raised to the power of 2 minus m. M is the exponent of the Paris law, minus A naught raised to the power of 1 minus m. So this is already quite a complicated equation, but it can be managed in a closed form manner. And here you see the variable delta sigma. If everything is held constant, given material, and given R ratio, so this is also then also constant, and is also directly related to delta sigma. Then you can determine nth lifetime for given crack sizes, starting crack sizes, and using delta sigma as the parameter for each run. Oh, that's the way how you do it. Okay, I want to stop here because the next step is has to do with inspection philosophies, and would like to leave that to the afternoon session. I hope the cafeteria is already open. Is that, does everybody know that? Huh? At 12. It takes 20 minutes to get there. No, okay, so let's continue a little bit. Because I'm hungry. Now, once again here, the diagram shows the two ways we go through the procedure. Now, here we have a crack size life diagram. Starting with A0, the crack propagates this way here, and so fracture occurs here, and here's critical crack size, and here is the end of life. Now this is what we predict by integration of our crack propagation equations. Okay. Now, inspection intervals. This is the predicted life for crack propagation situations. It may happen that a node is in the Zoom crack, but we can't find in the structure because either the resolution of our system is not big enough or not low enough, or the crack or the location of the crack is hidden behind something, and so our calculated residual lifetime is of no value, which means that below here we can't apply fracture mechanics. So here this ridge is not usable. This is our new A node, and this is the residual lifetime here. Safe assessment of safe in quotation marks, because you know all these predictions, please. Like we say in Germany, paper is patient. You can do everything on paper, and we have to accept the fact that all the parameters we put into our assessments have a certain amount of uncertainty, either real scatter, or we don't know exactly the accurate applied loads, and so on and so forth. And so that's why it is in quotation marks. So that's what I've written here. Of course, the predicted life has to be partitioned into inspection intervals. Now this serves for a check whether the actual or assumed crack has propagated, and if so, how far. So you should never rely on the predicted lifetime. If you can afford it, divide the predicted life or assessed prediction is something. It creates the impression of something accurate. It is not accurate. So partition the assessed or estimated lifetime into intervals in order to be safe, you know. Now this is the starting diagram, and we partitioned into two sections or two sectors. Sometimes people use 3 or even 4. So you have the first interval and the second interval. And the requirements, now the requirements for ADI emerge from the intervals given by regular downtimes. This would be the most convenient thing if your component or system, be it a chemical plant or railway equipment or aeroplane, has to go to, has to be grounded anyway for any other kinds of repair or regular thing, whatever. It would be ideal to perform the crack inspections at the same time. Otherwise, you as the responsible engineer would certainly have a problem with your management, because downtimes are always expensive. I told you before the break the example of the German high-speed trains, how disastrous the reduced inspection intervals are to the operation. Now, if this is the required lifetime, we calculate back. This is why the curve came down from right to left here. We calculate back, and oops. Very simple subject. The intervals given by regular down. We have to guarantee safe life, which means that the crack has to be detected, which will not lead to failure during the protected lifetime. And so, once again, we use the downtimes here for our inspection limits, for our inspection work. And we could have two different inspection NDI limits here. So we have a good life here. If it's here, then we have a problem because we have to do more inspections. Now, back to thin wall structures. Yeah. I told you already on Monday, just repeating here, that the application of fracture mechanics is usually based on high constraint conditions for plane strain. Whenever you look into the standards, be it an ASTM or a European or Chinese or Japanese standard, they all deal with thick walled specimens with a square ligament where they have high constraint, because fracture mechanics was created for relatively, at that time, relatively brittle materials, high strength materials for aerospace applications, where in some instances you have thick walls. Thick is not the absolute thickness. When we talk about a VAR aging steel, 10 millimeters are already thick, because here we do already have plane strain and thickness. The stress triaxiality depends, among other parameters, on the thickness. Had I a relatively soft or low strength steel, STE 350 or whatever, 300 millimeter thickness is just sufficient for plane strain. We machine such a specimen, CT specimen, 300 millimeters thick. We had a test machine which we could use to fracture the specimen. He never did it. Specimen was so expensive that we used it as something to show our visitors. Now, then came the thin-walled lightweight structures, the necessity to build excessively lightweight structures and to assess as accurately as possible the load bearing capacity, and we had no test method. I mean, the aircraft industry has something which is Stone Age fracture mechanics. Don't want to tell you. It's still being used as routine test, but that's Stone Age. And then the necessity came based on modern fracture mechanics to create a test method. And then we were able to feed our experience into ASTM and ISO. I told you on Monday for Delta 5 and CTOA, and how long it took to feed something that was ready from the beginning of the 80s, 1980s, into test standards of the 21st century. Now, thin wall components are plane stress conditions, and we have the transferability problem. And here on the right-hand side, I have a sketch showing, again, you saw it already on Monday, just to repeat, to refresh your memory for your competition this afternoon. And nobody panics, no? Okay. Here, bending versus tension. Bending has higher constraint than tension. Here, increasing thickness leads to higher constraint. And constraint is decreased when we keep thickness constant, but we extend the ligament here. And so this is something, by the way, that we found in our experiments. And so it's kind of a mess here. You know, you had to vary so many parameters. And so, like I said on Monday morning, an elegant solution is using numerical damage mechanics models. Now I'm checking the time again. Sorry for that. Okay. To finish here, these conditions and high degrees of plasticity have only recently been considered in the last 10 years or so. And we have new test standards in ASTM, ESIS is coming out next year, and ISO for specimens of low constraint. And it has already been available for more than 20 years in our research center. And an alternative is damage mechanics models. treat the transferability problem automatically. If you do a 3D analysis, you will end up with results of high accuracy. Now, I'm stopping here. I think we should have our lunch break, and I'm continuing at 1 o'clock. Is that okay? 1:15. We can take a nap. Okay, 1:15. So see you.